Miranda. Well, I wouldn't say it's going yet, but
I get it.
my normal response is it's going, but I'm not sure I can even say that yet. So there we go. Okay.
Yeah. The kids woke up at like 5:45, rearing to go, like screaming. It was awful. Terrible way to start the day. I do not recommend it.
I mean, there's something to be said for 0 to 60. I'm a 0 to 60 kind of person myself in the mornings when I'm having a good morning.
Usually, yeah, I am when I'm having a good morning. Like I start work at 6:30 normally, and like I love it. I get in there early. I'm like ready to go. But when it's like screaming children that won't stop screaming, no matter what,
that's another story.
Yeah. I'm not 0 to 60 in that situation. But your kids are back in school, like in person, right?
They are.
That's nice.
Wonderful. The bus stop is fantastic, and they got into the Boys and Girls Club after school, so I don't have to pick them up till 6 o'clock.
Oh, God,
so it's like 8 to 6. They're totally cared for, and I don't have to worry about them.
That's good. How old are they?
My youngest Valence just started kinder last Thursday.
Awesome.
And Dash is in 2nd grade.
Nice.
Yeah.
Oh, that's great. So they're both in school.
They're both in school. Valence is getting a little frustrated because they're in the Spanish immersion.
Okay.
And she doesn't like not knowing what's going on.
I can see that being frustrating. Yes.
And every time we tried practicing Spanish with her, like just using Spanish around the house, she would just get mad and start yelling, "I don't understand what that means."
You know I don't speak Spanish.
Exactly.
Oh, poor thing.
Yeah.
But it'll be good. I mean, it's great that they have that program.
Oh yeah, no, I love it, and our son is thriving in it. And frankly, knowing what I know about myself and my kids, like if my kids were bored in kindergarten or school, they find ways to not be bored. For me, when I was a kid, that was reading a book under the desk, but my kids are decidedly higher energy than I was.
Yeah.
So I have no doubt that they would make some teacher's life a living hell if they got bored. So it's good to keep them on their toes. Just throw them in the deep end; they'll be fine.
Absolutely.
Morning. Good morning, everyone.
I just got to say, I think I think the Giants
After last night?
I did. Well, I think I've always thought that.
That's fair enough. The only reason I don't hate the Padres is because I went to school in San Diego, and I have a lot of respect for San Diego because the entire city is transplants, right? So the fact they have like any sports teams that are, or any fans whatsoever is impressive. Because I swear, I think I saw more like Patriots fans that lived in San Diego when I lived there.
That's like any team playing the Patriots. There's more.
Well, that's true. That's true. But it would like Eagles fans, Patriots fans. Like there are more people from the East Coast in San Diego than people that grew up in San Diego.
Yeah.
And my roommates all grew up in San Diego, and so they really, really hated all the transplants. So.
We'll go through pretty much of the years because the same problems happening with last year's numbers in the morning.
Okay. Yeah, see if somebody can come down here. Oh, he might have just gone to sleep. No? All right, we're working on getting captions going.
Are you from San Diego or are you just like San Diego?
No, my dad's from San Diego. So I kind of got pushed into that way. My mom's from LA, so I would have to kind of.
Yeah, are you a Chargers fan too?
You know,
Raiders, oh, actually, look at your hat. Even
yeah.
though they moved, you're still.
Oh, yeah. Yeah, and my dad, he's really fond of the Chargers once in LA. Like, he's really good
Yeah.
about it.
Yeah, my friends are too. They're not very happy with Spanos.
I'm okay with the Raiders going to Vegas because out of all the places they could have gone, I think Vegas suits the Raiders the best.
It's
Yeah.
true, and it's not like they moved across the country. You could still make, especially from up here, you could make a weekend road trip to Vegas, not that much farther than going to Oakland,
Yeah,
frankly.
and honestly, I think I would rather go to Vegas than Oakland. Every time I've been to Oakland, it hasn't been a good experience.
It's true, they were still in the Coliseum, right?
Experience. I love Oakland and I can totally do without Vegas.
Yeah, the Raiders look good this year.
So far,
Yeah.
I was really proud about it. I'm a Ravens fan, but it's just like, it sucks.
I'm married into a Minnesota family, and so they're all Vikings fans, and disappointment and heartbreak is just bred into that team. They've already had 2 heartbreaking losses this year out of 2 games.
Yeah.
And it's just like, the second, they missed an extra point in the first quarter. And my wife looked at me and said, they're gonna lose this by 1 point. And they lost it by 1 point.
Are you from Baltimore?
I lived in Baltimore, I'm from the DC area.
Oh, I lived in Baltimore too.
Yeah,
Yeah.
I lived right above Charles Village for a time in the Parkway.
Yeah.
Yeah, by the paper man.
Oh, yeah, I lived in Butcher's Hill for like 2 years and then Canton for
Oh, nice.
for 5 years. Yeah, we're actually going in a few weeks
Any
to
luck?
sell our house there.
Nobody said.
It's like.
Okay, well,
bittersweet, but
Let's see
it's
if I can give you a hand with this real quick. We've got, this is set to, looks like a frequency. And do you see the frequency?
I'm not sure how to get it, like, feeding to her.
Okay, no worries.
But I have a Skype open, she's messaged me, and, this is,
Is mine paired with Skype? Chance? Maybe ask her if she knows how to do that. Oh, you know what? Maybe it's like selecting your microphone in Zoom. Open up Skype real quick. Let's see, let's see.
I
So
don't have her
Click
time.
on the dot, see if that's
Florida.
settings.
It's like in between Miami and Fort Lauderdale.
What up there?
Really?
Yeah.
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 I wonder if we like went to the same high school or something. It's like a.
Are you on video?
Like my graduating class, I think, 150 kids.
That's your
But
camera.
my brother still lives in Miami. And I went to school in Boston and then lived in Baltimore, going to my
Okay.
first job, and that's where I met.
I don't know which microphone it's receiving.
I don't know.
It's like so affordable and it's so
Okay,
many
like,
like
guys are using your microphone, and like everybody's
Okay.
at the same stage.
But that could be this
I loved
microphone.
it. And I love going to Orioles games, like you have.
They're so cheap. And you can bring your own food.
it doesn't sound like you want to be.
Yeah.
Okay. Yeah, I would think so. Okay, well, it seems like it's receiving. Ask, maybe go back to the chat real quick and see it. You can tell her that your computer is receiving the microphone from the lapel mic and see if she has any ideas. All right, while we're troubleshooting this, everybody can, just to recap where we started, and I think that this is going to be less in the way, this microphone stand, or this camera stand. Is that better for everybody? It's only going to capture this board right here, so if you're going to have to follow along on the slides if you're watching the video later. But I think that that'll work best for now. So to recap where we left off, we were talking about formal charge and how we could look at the different number of electrons that an atom controls, so to speak, and use that as a way to give that atom a charge by comparing the number of electrons something charge or controls to how many valence electrons it has when it's on the periodic table. So, and the main point of that is that, generally speaking, we can make the assumption now that if a carbon has 4 bonds, it's neutral. So we're just sort of flipping the way we're looking at these. Instead of looking at it from the point of view of counting electrons, we're looking at it from the point of view of this is the standard situation where it's neutral, because most atoms are going to be neutral. That's how things are most stable usually. So carbon generally forms 4 bonds, nitrogen generally forms 3 bonds, oxygen generally forms 2 bonds, and hydrogens and halogens generally form 1 bond. If it's not one of these cases, when I say usually, I mean when it's neutral. If one of these is not true, then either that atom has more electrons than normal or fewer electrons than normal. If we assume it's got a full octet. If it doesn't have a full octet, then that's a situation we call free radical, where you've got an unpaired electron, and we're actually going to state that explicitly as well. We'll do a whole chapter on those later. But for now, we're just going to be talking about electron pairs, and we're always going to assume everything has a full octet unless otherwise indicated. And so, what do we know about a nitrogen that has 4 bonds instead of 3?
Probably an ion.
Probably an ion. Which direction? Ions could be positive or negative, right?
Positive.
And why?
Because it can form another bond, so it's going to want another electron. So it probably has less than normal.
That last part was what I was looking for. Specifically, so if nitrogen, either way, nitrogen's going to have 4 or 8 electrons around it, right? It's just a matter of if it has a lone pair, it's controlling those outright. So if it has a lone pair and 3 bonds, it's got 5 electrons that it controls. If it has 4 bonds, it's still got the full valence, but it's only controlling 4 instead of 5. So it has 1 fewer electron that it controls. So a nitrogen with 4 bonds is always going to have a plus charge. All right, Anna, any luck with that?
I tried starting a Skype call and turning off the camera, but
Okay.
the captions aren't super accurate, so
Okay.
I don't know if she was getting it from that one.
Okay, then I'm just going to keep projecting as much as I can, and let me know if you don't hear anything.
Yeah, I'm gonna try to go to the VRC again today
Okay,
and figure it out.
yeah. So here's our 2 options. If nitrogen has 4 bonds, this is the one that seems more likely, right? This is the one we already talked about. It seems intuitively, you guys have a little bit of chemical intuition at this point. Maybe not OChem intuition yet, but you kind of know what's plausible with a lot of these situations, even if it's hard to articulate. Because if nitrogen has more electrons than normal, that's one of those few absolutes that I gave you yesterday or on Tuesday, right? You're never going to have more than 8 electrons on something on the second row. The second row of the periodic table, that's a hard rule. Carbons will never have more than 8 electrons. Oxygens will never have more than 8 electrons. Right? So that means that we can count bonds as a way to determine the charge, as long as we're assuming everything has full valence, which is almost always going to be the case. All right, so let's practice going through these and see if anything has a formal charge. Any of these atoms should have a formal charge. So the number of electrons something controls minus the number of electrons it has on the periodic table, valence electrons.
Would say -1.
So let's,
We're positive.
so aluminum with 4 hydrogens around it. In this case, the aluminum's got a full valence. It's controlling 4 electrons, and on the periodic table, aluminum only has 3 valence electrons. So yes, the aluminum has a -1 charge here. The hydrogens have any charges?
No.
No. Hydrogen with 1 bond is always going to be neutral. In this case, because the hydrogens are actually more electronegative than the aluminum, if you think back to your inorganic nomenclature from Gen Chem, if you put a hydrogen with something that was less electronegative, then the hydrogen has the negative charge out of this bond, right? If this was a polar bond, the hydrogen would have the partial negative. So we would actually name this as a hydride. Remember, IDE is how you indicate something that has a negative charge or that's the partial negative in a compound. So this is actually aluminum hydride. And we actually use this a lot in organic chemistry, we'll see later, because it's actually really helpful and useful in terms of synthesis in organic chemistry to be able to give a negative charge to a hydrogen. Because if you give a hydrogen a negative charge, it can attack a positive charge somewhere. And that's the fundamental background of almost every reaction that we're going to see in this class is negative charges attack positive charges. Right, so this is a common molecule for the reason that it gives us really good hydrides that can then go attack something that has a positive charge. Any others? Let's see. How about on B? Anything? How about, that's awful. Wow.
Those 2 markers are.
Yeah, I was just looking for something that was going to be dark enough that you could see it on the camera. There you go. Yeah. It turns out there's actually like different brands of whiteboards are paired with different brands of markers. If you use the wrong brand, it doesn't erase properly.
A brand album.
Sounds like I saw an interesting headline about Apple. Apparently, the European Union is forcing them to adopt USB-C ports in Europe
Good.
by the end of next year or something like that. So they might actually get on the bandwagon with USB by then, which would be really nice. I mean, it doesn't affect me because I try not to buy Apple products, but for other people, I like it in principle. Hannah?
Why do you think that like different brands matter? I would think maybe it was like a difference of like being water-based or alcohol-based.
Most dry erase pens are water-based, especially the low odor kind. It's more about the ink and the surface of the whiteboard. Different surfaces and different finishes are going to stick to the ink better and make it harder to erase. All right. Before we got off on that digression, H3O, the oxygen's got 5 electrons, right? 6 on the periodic table. So that oxygen's going to have a plus charge, right? Which, and that one's one you should be familiar with from Gen Chem, right? That's good old hydronium. H3O plus, right? pH. Ringing any bells? How about over here? I know the hydrogens are all good here. Carbons are also good. So nitrogen's controlling 6 and it's got 5 on the periodic table. So that tells us the nitrogen's gonna have a negative charge in this case. And you know, when molecules are typed out and everything, it's pretty easy to see the lone pairs. In your notes, at least when I'm writing on the board, I always circle my lone pairs with the little loop to make sure that it's visible. It's really easy to lose 2 dots, especially when the whiteboard doesn't erase cleanly. So it's not a bad habit to be in, and that also reminds you about the fact that they still take up space. We'll get into Vesper geometries here in just a minute. It's not a bad habit to be in. So how about down here?
Oxygen has a +1.
Oxygen's +1. 3 bonds to an oxygen makes it +1. -1.
Right.
It's got extra electrons, so it's a minus. Damn you, Ben Franklin. All right, so, and we're gonna see that really commonly since this is OChem, we care about carbons more than anything else usually. And a carbon that has a negative charge is always gonna have a lone pair. A carbon with a plus charge, which we call a carbocation, is actually going to be one of the few cases where we don't have a full octet. Right? Because you can't get carbon that can't have a plus charge by making an extra bond because carbon already has 4 bonds, right? You can't make an extra bond with a carbon because you can't have a carbon with 5 bonds. That's the cardinal sin in organic chemistry. It's drawing a carbon with 5 bonds. They call it a Texas carbon. Nothing against Texas, but everything's bigger there, right? So a Texas carbon, there's no faster way to put anybody grading organic chemistry in a bad mood than to draw a carbon with 5 bonds. And so if we can't have 5 bonds, how could carbon have a positive charge?
Lost an electron?
It lost an electron, and typically not just one though, right? You know, if we think about methane, you can't just lose 1 electron from this, right? Because if you lose 1 electron, you're going to be breaking a bond, essentially. So typically, if you have a carbocation, it means that you actually only have 6 electrons around that carbon. And this is going to be one of the very few cases in this class where we actually have an incomplete octet. And for carbon, if you put a positive charge on it, that is telling you it's an incomplete octet. When oxygen has a positive charge, it just means it has an extra bond. Same with nitrogen. But when carbon has a positive charge, it means it's missing electrons. It has a vacant spot, which will wind up being really important when it comes to moving electrons around. You gotta have a place to put them, right? All right.
So that last one?
Yes.
That you said was positive?
So this would be the positive where it doesn't have full. So that's extra electrons. So negative. So if this is a carbocation, that's a carbanion. Remember, anion stands for a negative ion. And the way chemists like to name things is just slap prefixes together. Frankly, I'm even surprised that they bothered with the extra syllable in carbocation and just did go with carcation. All right, let's talk a little bit about isomers. You guys saw this in lab the other day. An isomer just means anything that has the same molecular formula but has a different arrangement of atoms. Right, so constitutional isomers are the most common, where you actually physically switch which atoms are hooked up where. both of these are still neutral compounds. Everything has a full valence. So everything's relatively stable, but they behave very, very differently because you have different kinds of bonds present. So, and if you total up all of the atoms, you're going to wind up with C2H6O. However, they have very different physical properties, very different medicinal properties. Dimethyl ether is not the ether that they use as an anesthetic. That's diethyl ether. Mostly too, because it boils at such a low temperature. So it has similar effects on the body, but is less desirable for other reasons, for other physical reasons. And ethanol is good old drinking alcohol. And so clearly very different physiological effects just by switching where the oxygen is. Yeah.
So, you know how some alcohols that you can drink are flammable and others aren't? What's the difference between that?
Concentration. You have to have alcohol above, in theory, it has to be about 50% of the mixture, but in reality, with using a lighter, it would have to be, it's more like closer to 75% of the mixture. Otherwise, it won't boil. It won't burn. So that's typically you see it with really high proof stuff, 151, things like that. But all drinking alcohol is the same compound. It just varies what else is around to give it different flavors and what concentration. I guess I shouldn't say that. They're the cheapest of alcohols, especially hard liquors, typically have other alcohols mixed in that are poisonous. There's usually a little tiny bit of methanol mixed in with cheap vodka, not on purpose, just because it costs more to get rid of it than the vodka costs. So, rot gut, plastic handle vodka will give you a nasty hangover, and that is supported by the science. Because it has more methanol than should otherwise be present. All right, so we're practicing drawing constitutional isomers. This was one of your assignments from lab, right? It gave you a formula and you had to practice some, finding different structures that'll work. We have 3 carbons, 7 hydrogens, and a chlorine. How many bonds does the chlorine want to make normally? 1, right? It's a halogen. So basically what we have here is you're going to be replacing a hydrogen with a chlorine. So C3H8 is propane, and it's going to look like this. There's really only one way to arrange it. That's C3H8. Are there any constitutional isomers there?
I don't think so.
I could do that, but is that really a different molecule? No, because remember these things are three-dimensional objects that are free to rotate around in 3 dimensions. They're not really stuck at 90 degrees either. These are tetrahedral. So really, this is just a less convenient way of drawing the same thing. I say less convenient just because you can see things start getting stacked up on top of each other there. So what changes if we remove a hydrogen and replace it with a chlorine? A little bit of the shape, yeah. Chlorine's got to be bigger than hydrogen. It's got more energy levels, right? Even if it still only does form 1 bond.
It'll have lone pairs, right?
It'll have lone pairs around it. Does it make it so that we could have a constitutional isomer?
Yeah.
Why do you say that, Sarah?
It would be different if you put it on one of the end caps.
Yes. So putting chlorine here versus here is not going to change things because it's both attached to the second carbon. But in order to put the chlorine over here, we actually would have to break a bond. We can't do that just by twisting things around. Because now we have the chlorine attached to the carbon at the end of the chain, as opposed to having the chlorine attached to the carbon in the middle of the chain. Right, so when it comes to figuring out the different numbers of constitutional isomers, it takes practice. And we will continue to practice at that. And there's not, I'm sure that there is a combinatorial mathematical way you can predict based on the constraints, how many isomers you could make. But that's beyond the scope of this class. That's upper division math, really. Combinatorial math is really cool stuff, but it's also upper division, so we're not gonna get into that. Hannah?
Is it like another type of isomer if you stick it on like one of the ends?
So I'm glad you asked that. So if we put the chlorine here instead.
Yeah.
So this is going to transition us nicely into talking about Vesper geometries in a minute. But remember, this carbon's tetrahedral, right? It's not really 90 degrees. And so really you could, it's really got a shape that looks like everybody remember this style of structures? So the dots mean it's going into the board, the wedge means it's coming out of the board. So if it really looks like this, then we can put the chlorine in any of these three spots just by twisting this. So it doesn't matter where we draw it on our structure, as long as it's attached to that same carbon. All of the positions attached to that carbon are identical. It's just which of the three is it attached to. Let's do the same thing over here, and just to practice this some more. Is that a different isomer? If I put it on the left-hand carbon instead of the right-hand carbon? No, because if I took this, remember this is a 3D object, right? If I took it and I flipped it like a pancake, the chlorine's attached to that side now. And so is it attached to the carbon at the end or the middle is what gives us our isomers, not the left carbon or the right carbon.
So that doesn't necessarily change the molecule itself, just the characteristics of the molecule?
It does, we're going to name them different. Those are two different compounds. This we call, and we'll get into the rules for naming things in a little bit. We would call this 1-chloropropane. Pro is the prefix that means 3. So 3 carbons, so propane, and 1-chloro means that you've got a chlorine attached to carbon 1. If we put it in the middle, this is 2-chloropropane, which is going to have different properties. So basically, when our rules for nomenclature in OChem are always going to be, we need to be able to get to the exact right molecule, the exact right structure, even if it's drawn in a different arrangement, from the name. Every name must be a structure, even if it's drawn in a different arrangement, from the name. Every name must be unambiguous, so that there's no way that I could draw the wrong chloropropane isomer. So we'll keep adding rules to our nomenclature as we start getting more and more complex molecules, so that we can say unambiguously, this is the structure that goes with that name. And yes, isomers are different compounds. How about C4H10? That's one, right? The easiest isomer is almost always just going to make a straight chain of carbons and add hydrogens until you get to the right number of hydrogens. If you're missing hydrogens, usually that'll mean something like there's a double bond or a ring present. Are there any constitutional isomers here? We could get 4 carbons in a row. If we put it here instead, I'll stick to the structure. And put the hydrogen over here. That's still C4H10, right?
But isn't it like what you said before, it's just a more complicated way of drawing it? It's still like the same.
No, because now you don't have 4 in a row. There's no way you could count it so that you got 1, 2, 3 and get a 4th carbon without jumping back over here, right?
So this would be an example of branching.
This is an example of branching, exactly. This is still propane here. It's a propane with a branch sticking off of this main carbon group. And again, it takes a while to get to know how to see what is a different isomer and what is just a different way of drawing something. But your number one tool is, if you can't count in a continuous line and get the same number of carbons, it's a different molecule. If I put the CH3 up here, that's an example of just a different way of drawing it. Because drawing it up this way versus down is the same. It's still attached to the second carbon though. What if I took this and I put it over here? Then it would be the first one that we had flipped, right? So still, as soon as we move this to one of the ends, now we can count 4 in a row and it's butane. When you have attach that last carbon to the middle, now our longest chain is 3 and it's a propane. What if we start adding we add another CH3 group, we add another carbon to it. Make it C5H12. And we're starting to get to larger things here, so I'm going to go to condensed structure, or actually I typically use what's called a Kekuli structure. Remember August Kekuli, the one who took his inspiration from Egyptian stories of the Ouroboros? Remember, I told you that the simplest isomer is almost always just going to make a straight chain and make sure you have the right number of hydrogens. So 1, 2, 3, 4. And carbons at the end are usually going to be CH3s because you need to add enough hydrogens to make 4 bonds. Carbons in the middle are going to be CH2s because they already have 2 bonds. So here's one isomer. Do I have the right number of hydrogens? We should, unless I miscounted something.
Yeah.
2, 4, 6, and 6 for the ends, so 12. If we do the same approach, and move a CH3 over to the middle of the chain, now it's another isomer, right? So now we only have 4. Even if we count the other way, 1, 2, 3, 4, it's still 4 in a row with a CH3 attached to second from the end.
And it could also be on like the other middle carbon, right?
And if we did that, still 4 in a row. with a methyl, or sorry, with a CH3 attached second from the end, right? So that's the flip of the one we drew a second ago.
Oh.
And so one of the other big rules of naming these things is you count from whatever end is closest to your branch. So this would be 2-methylbutane. And again, don't worry about the names right now. The important thing is that 2. This has the CH3 on the second carbon. This also has the CH3 on the second carbon. You just start counting from this side. Right, it's the same molecule flipped over. Right, so it takes practice to be able to see these things in 3 dimensions. And it's actually really interesting. I always bring this up because I always got told I was wasting my time playing video games as a child. But they've done studies that people who play video games, especially video games that in 3 dimensions, actually improves success in organic chemistry classes, because you're already used to visualizing things in 3D and what happens if I move the camera over there, which is basically what we're doing with a lot of these. Is we're going to draw it and then we're going to picture it in our head and flip it around. And so, and if you didn't grow up playing video games, then you're still okay. It just takes some practice to get used to it. We're going to leave the others for now. We'll come back to them in a little bit. We'll talk about D. We're going to talk about Vesper geometry, but before that, we're going to talk about bonds some more. So Linus Pauling, one of my favorite chemists of the 20th century, one of 2 people, Marie Curie's the other one, to receive 2 Nobel Prizes in separate fields. He got a Nobel Prize in chemistry and then a Nobel Peace Prize for his work in nuclear disarmament. And he lived in Big Sur, hung out with all the folk rock musicians and Bob Dylan and Neil Young and Big Sur in the 60s. Pretty awesome guy. His main contribution was that he said, okay, well, we have a bit of an issue with our bonding theory. He said, okay, well, bonds are formed when partially filled orbitals overlap with each other. That whole idea of covalent bonds was him. But the problem with that, and this works for simple molecules, the idea that if you have a hydrogen atom and a hydrogen atom separated by an infinite distance, they both have one vacancy in their valence shell. And as you bring them closer together, those valence shells can start to overlap, and you wind up with both of the hydrogens being able to act like they have a full valence. And so what this does is it creates this shape of this graph. This is a potential energy surface, where at the bottom here, it's going to be the most stable, where you're at the lowest energy configuration. There's some distance in between these 2 atoms where there's the maximum overlap you can have in between these orbitals before the 2 nuclei get too close together and start pushing each other apart. All right, so this kind of goes up to infinity just about as you get these nuclei closer together, because positive charges repel each other. So it's sort of just balancing out of the different forces that creates this bond distance. And so the other way we look at that is from the point of view of constructive interference. And if you look at the atomic orbitals of water, the oxygen's got a p orbital, and a hydrogen's got an s orbital, and as you bring them closer together, those orbitals can start to overlap and form something that looks like this, where you have an area in between both nuclei where you can find both of the electrons. Therefore, it's in both valences at the same time. Hannah, did you have a question?
Yeah, so did this guy figure this out just by doing the math, or was there an experiment that allowed him to figure this out?
Partly it was the math, and partly it was the fact that they needed some theory to explain why oxygen makes 2 bonds. to be most stable? And why would it make a bond? And so he basically was taking this magnetic repulsion and the idea of orbitals being energy levels. And he came up with the idea of that these orbitals, if you mix them together, actually get to be lower in energy because you can put the electrons in both places at once, kind of. Right?
So when I read constructive interference just now, I thought about light, and I'm just curious as to why they would name it this. Is it related because because of particle wave duality?
Partly. Part of it is the fact that these electronic orbitals are wave functions. And these waves, they're probability distributions really, right? And probabilities, these probabilities, when you bring them closer together, can have constructive interference if they're in phase. If the blue and the green were flipped here, then you would have destructive interference, and you have what's called an antibonding orbital. And the other reason that light ties into this is the energy difference between the bonding energy and the antibonding orbital's energy is the wavelength of light that it will absorb. So you can actually break a chemical bond by shining the right frequency of light on it because you bump an electron from this orbital into one where there's destructive interference instead. So it is all tied together, and it is that particle wave duality, and it is tied to light as well. And here's our antibonding orbital. So if the phase is flipped, it's a little bit like a positive and a negative, but we don't want to use that term because it's all electron density, and electrons are always negative in terms of charge. So we use the term phase for it, and so they're in phase when it's the same color. Basically, when you can have constructive interference, they're in phase. When they're out of phase, you get destructive interference in an antibonding orbital. And so the problem with that is it works for oxygen, it doesn't really work for carbon. Because if you look at carbon's atomic orbitals, it only has 2 partially filled orbitals, right? Which, according to this valence bond theory, says that we should only be able to make 2 bonds with carbon. But we know that that's not what we actually see. So, and here's where Pauling really took a step above. Pauling was he was kind of at the forefront with some of the other bonding stuff, but he wasn't really wildly ahead of the pack until he came up with this idea that, well, what if we mix these together? We're mixing these atomic orbitals together to make bonding orbitals, right? So what's stopping these atomic orbitals from mixing together with themselves? And so they called that a hybridized orbital. So in order to accurately model the ability of carbon to form 4 bonds, we need to add some linear algebra. Not everybody's had linear algebra in this class, so we're not going to actually do the math by hand.
Would that be polyspin matrices, or is that different?
That's a little bit different. We'll get into that. Not too much in this class, but this is going to be a common theme in chemistry. Every time you take a new chemistry class, we're going to tell you, well, that was okay for Gen Chem, but really we need to get more into it because that was kind of wrong also. In order to follow both the Octet rule and the Aufbau principle, the Octet rule is filling valences is good. The Aufbau principle is you fill from the bottom up. We hybridize the orbitals. And hybridizing the orbitals just means these orbitals are just mathematical functions, right? And you can mix mathematical functions together to make new functions, can't you? And each of those functions is going to be, each of the components of those functions are going to be a little bit different. You can kind of change how much you have of this function versus that function by treating it like a weighted average, basically. So if we allow these different functions to mix together, we can actually get 4 orbitals that are all degenerate, that are all the same energy. It makes the p orbitals go down in energy a little bit, the s orbital comes up in energy a little bit, but the result is you wind up with 4 orbitals that are the same energy. And if you have 4 orbitals that are the same energy, remember Hund's rule was the one that said you fill them all up before you start doubling. So these hybridized orbitals are what allow carbon to form more than 2 bonds. And it also winds up, if you look at the shapes of the orbitals, that's also what accounts for Vesper geometries. Because if you take an s orbital, which just looks like a sphere, and you take a p orbital, which looks like a figure 8, but part of it's in phase and part of it's out of phase with the s orbital. On this side, they're going to sort of partially cancel each other out. This side gets smaller. But this side, you're going to have constructive interference, and they get bigger. And if you actually do it with vectors, and you have these p orbitals pointing along all 3 axes, you wind up with 4 functions that are pointed 109.5 degrees from each other. So you actually get a tetrahedral geometry by adding 3 p orbitals with 1 s orbital, and letting constructive and destructive interference run its course.
What's the mechanism that dictates these hybridizations? Like, it almost sounds like the atoms just do it themselves, but there's got to be something that causes this to happen. Is it a force? Like, is it the weak? I would say it's the weak nuclear. That's my guess.
So we're luckily for us in OCHEM, we don't need to worry about nuclear force or either of the nuclear forces. We're going to stick strictly to electromagnetism. We're going to ignore gravity for the most part as well. So we're just electromagnetic in this class. Basically, the same reason that bonds form in the first place was because it allowed it to get to a lower energy state, right? Lower energy states are more stable. By allowing the orbitals to hybridize, now we can form 4 bonds. Bonds are more stable than not having bonds because it allows us to fill the valence. So it's something that happens spontaneously. It's this weird sort of mathematical thing that happens just because that's how energy is minimized. And one of the fundamental rules of the universe is low energy states are more favorable than high energy states. It's one of the very few times where I will just say because that's the way it is, because I don't know how to say it anymore than low energy is more stable. That's just the way the universe works. But yeah, it seems like the way we describe it is this really complex mathematical thing that seems like it's all these operations that have to happen. But really it's the same thing. It's a little bit like saying, well, why does constructive and destructive interference happen? It just does. When you put waves together, they cancel each other out. All right. Couple more minutes. We're going to go just to finish this thought about hybridization. We didn't use the term SP3 in Gen Chem, right? Did we talk about that at all? Maybe very slightly, very quickly, when we did Vespers. So basically, we just have a way of, it's similar to doing electron configuration. We can describe the hybridization, which also describes the Vesper geometry. It's just another way of saying the Vesper geometry, just by saying how many orbitals and what type are mixed together. So if we mix together 1 s orbital and 3 p orbitals, we call that sp3 hybridized. The 3 is the superscript, but we don't say it as cubed, it's sp3. And that means that carbon can make 4 bonds because you have these 4 orbitals that are all the same energy, all partially filled. If one of those bonds, and so those single bonds are what we call sigma bonds. When you just have these orbitals overlapping with each other in really simple, with that function we were looking at earlier with the constructive interference, that's a sigma bond. The problem is that if you need to make a double bond, you can't have two sigma bonds between the same two atoms because the space in between the two atoms is already taken up. So if you're going to have a double bond, it has to be a pi bond. And a pi bond is going to look like this. You've got a sigma bond in between the two carbons, so that your second bond can't be in that same physical space. So your second bond has to be above and below. And these sp3 hybridized orbitals don't have the right shape for that. An sp3 hybridized orbital has this sort of balloon-looking shape that kind of looks like this. And so if we have two carbons, both with sp3 hybridized orbitals, the sigma bond is going to look something like this, where you have these two things sort of overlapping. Well, if we already have the sigma bond and we want to make another bond in order to have more electrons there and fill more valences, we actually need unhybridized p orbitals to do it. Right? Those unhybridized p orbitals are going to stick up and down. So remember, the nuclei are at the center of these. And so if you have, if your phases are right, you're going to have constructive interference above and below the sigma bond now. But you need unhybridized p orbitals to do it. The shape and the geometry is not right if they're sp3 for this to happen. So to make a double bond, to make a pi bond, it's not where the sigma and the pi actually come from, but I always just remember sigma equals single and pi equals p orbitals. A pi bond happens when you have an unhybridized p orbital on each side. And so you wind up with a different hybridization because you weren't able to actually mix all three of these p orbitals together. You were only able to mix two of them in with the s orbital, right? So if you have a pi bond present, it's not sp3, it's sp2. And if you had two pi bonds, that would mean you had two p orbitals that were not able to be mixed in. And so you would just have sp hybridization. Right, so, and we're not even going to get into the d orbitals for this because we only care about the second row of the periodic table. There are no d orbitals there. So we don't need to worry about more complex geometries for this class. And our hybridization really only goes to sp3, which is going to give you a tetrahedral shape. It means you've got 4 sigma bonds attached to that central atom. sp2 means you're going to have 1 pi bond and usually 3 sigma bonds if we're talking about a carbon. But remember, lone pairs still take up space the same way as a sigma bond, though. So if you have 3 electron groups around the central atom, it's always going to be sp2. If you have 2 electron groups or electron domains around the central atom, then that means you only were able to mix in 1 of these p orbitals. If 2 of them have to stay unhybridized to make pi bonds, only 1 of them gets mixed in, so you would just have sp. And so what that would look like is, for instance, carbon dioxide. I'll finish this thought, and then we'll break and come back and we'll practice. And the red's almost as bad. So if we have carbon dioxide, the Lewis dot structure looks like, wind up with oxygen, oxygen, right? And then our remaining electrons, we would start by doing it like this. Carbon doesn't have a full valence, right? So we would need to make some pi bonds here. So in the middle, we have a carbon that has 2 pi bonds. So if I erase these lone pairs and redraw everything as orbitals, in the actual shape of these bonds, you're going to have a sigma bond here and a sigma bond here, and this would still have the other little pooch pointed the other direction that's out of phase. I'm just not going to draw it. This is going to get complicated enough without it. So these are our sigma bonds. There's our first bonds that form. Then, in order to make two pi bonds, first we make a pi bond. It's kind of handy that it didn't all the way erase. There's a pi bond between carbon and the right-hand oxygen. If we're going to make another pi bond, it can't use the same orbitals here, though, right? This p orbital is already used up making a pi bond over there. So the other place that we can put the electrons is, remember that there's 3 p orbitals that are all pointed in 90 degrees from each other, right? There's a p orbital that goes in call this the x direction. There's p orbitals that go in the y and the z directions as well, that are all 90 degrees from each other. So we wind up with something that, if you can visualize this, comes straight out at us and into the board behind us, or behind the board. So these can form a pi bond that's perpendicular to this one. If this pi bond is straight up and down, this pi bond is in and out of the board. And that only leaves one p orbital left to hybridize to make those sigma bonds. So the number of the hybridization of this middle carbon would just be sp. The hybridization here, and I remember this being really, really confusing and wanting to just move on and when I first learned this, but we're going to use these terms a lot, so we're going to get practice with it because it's actually easier to communicate if you just say sp2 instead of saying trigonal planar every time. The lone pairs on this oxygen are still taking up space, right? One of them is, here we can do it this way. One of the lone pairs is going into the board, one of the lone pairs is coming out of the board. So this oxygen has 3 electron groups, 3 things taking up space around it, right? In effect, it kind of has 3 sigma bonds and 1 pi bond. Even though there's nothing on the other side of these lone pairs, they're pointed in the same direction like a sigma bond would be. So that means that each of these oxygens is trigonal planar, and I'll refresh all of these terms in a minute as well for the geometries, which means each oxygen is sp2. This oxygen has the same thing. Its pi bond is going out of the board and into the board, so its lone pairs are sticking up and down in the plane of the board because they have to be perpendicular to the pi bond. So if the pi bond is like this, the lone pairs are sticking here and here. But it also has 3 electron groups, right? Which means it's also going to be trigonal planar, and it's also going to be sp2. So every atom, to go along with shifting our frame of reference, every atom is a central atom. Every atom has an electron geometry. Every atom is going to have hybridization, how many electron domains there are around it. Right, so when we come back, we'll go over this one. We're going to assign hybridization for every atom in here. It's not going to take as long as you think, because once you get the hang of it, it's actually really straightforward to discuss hybridization that way. So let's come back at 10 after. So before we break, Brad.
So I'm sure the drawing doesn't really give it justice, it's not 3D, but I'm just curious, like with all these different geometries in which these bonds are headed? Like, how are the interaction with the electrons shared? It seems like to me that they'd be overlapping at some point, but we know that doesn't happen.
Well, so these electrons are overlapping. Their orbitals are overlapping. That's what makes it a bond. And if these electrons happen to fluctuate forward, like if this whole thing, the whole red orbital started rotating forward, well, that's going to push on the green ones and push the green ones away. So if this starts rotating forward, the green one starts rotating down. So this whole thing is very dynamic as far as movement goes. Anytime something moves, it pushes on everything else. You think about it, if you have a spring mattress, anytime somebody moves anywhere on that mattress, everybody feels it and sort of rolls, especially if it's a saggy mattress, right? That's sort of how these things work. All of these bonds are, you can think of them like being springs, where everything's attached together. You shake something over here, that shakes too. All right, 12 after, and we'll keep practicing with this.
Oh, just getting off to a start. Just getting started. Pretty good though. I'm doing good. I feel so happy to be back in this environment. You don't know it. Totally. Yeah, it's nice. We were here for a little while, you know. Pretty nice. It felt so weird. Yeah, I feel like I remember there was a time I was taking Bio 110 and just like so stressed out about like all this stuff I had to have memorized. And I remember just like sitting at my desk and just feeling like steam coming up my ears as you walked up and you're like, hey man, are you okay? So there's like that sort of thing where it's just like, little things where it's like students sort of helping each other out in like little things like that that you don't get from like the virtual thing, but also That's a good point. I feel way less nervous sitting on my couch.
That's a very good point.
Taking notes and like, you know, like being in person here like this, it's sort of makes me
It's a little
a bit nervous, and especially like starting school, you know, that was like a whole thing. It was like, oh, you know, like, in one sense, cool the environment, for learning, but in another sense, it's like, you know, Jerry, you want that.
Yeah.
But that's where it dies down.
Yeah, I think it just takes a little time for that to kind of lose its momentum or whatever.
But I mean, ultimately, it's like there's pros and cons to everything. So.
Yeah.
It is not working.
It's that you kind of
Others-
step outside the comfort zone a little bit.
So,
They said that they would be on standby.
yeah, like.
So I have Skype open here. I messaged with them a little bit on Skype, but mostly messaged on the captioning app.
Does it feel
Also, I mean, like last quarter,
So it works.
Oh,
I was
That's
doing
how fast
a
it stops.
pedestal for class, and also a chemistry project. So I was here, like,
I just said don't worry about it because it was alerted.
Oh,
And I
yeah,
said
don't do
that I-
that, because when they do that, then they go away. So then I can't come in here
you know,
and try and.
Yeah.
here's my.
They said that they would be on standby so that I could talk to them
First time
after
we
class.
realized that they were doing anything like on here. Well, no, that's not true. I do some classes around campus, but
Yeah.
I'd like to just.
Okay, and are you calling
I
in?
should probably branch out and do other stuff.
Yeah. I did
Expand
the,
the horizons a little bit.
Are you supposed to be talking to Sarah?
yes.
Okay, so, you have a microphone?
Yeah.
Right now you have it set
I
to
mean,
default communication. You need to go to your on USB,
Yeah, this is,
PNP.
Oh, okay, see,
Okay.
down here, in like the sound settings, it said it was on, but it wasn't on the right
I was trying to
button.
do it.
Yeah, so just make sure you're on USB, and then hopefully, because that's what you learn, hopefully that will get them to hear. But now I'm feeling they went away.
Nice.
Stuff.
Yeah.
Ready to go right there.
Yeah.
Cool.
That kind of work is pretty inspirational.
Oh, yeah.
I wouldn't like want to put it in fun, but it's interesting to know.
Yeah, that guy's, the way he thinks about things is pretty fascinating.
Yeah.
Definitely a personality.
This was actually used selectively to destroy the dopamine.
She said she'd be on standby until like, I knew
Don't,
when
you
you
know,
were on the side.
That's all the sympathetic.
Where,
It's like they use that in studying Parkinson's.
Oh, okay, yeah. So they want to like create a problem in the system and then try to fix it sort of thing?
Right, well, more to study, to produce like a clinical model, so to study what's going on neurologically.
In mice, not humans. We're not
Yeah,
purposely
experimental
using
animals,
this.
yeah, not
Yes.
humans, yeah. You would very much not want that.
I just saw the disconnect happening. No.
Yeah, thinking. Yeah, it's pretty interesting, man. I like it. One of my favorite parts about doing the research project is just kind of immersing yourself.
So the call is not going.
Yeah.
Ended.
That
And
was
so
pretty
they
cool,
don't
the
hear
neuroclimate
anything.
and stuff, neuroclimate.
Yeah, I like doing that.
Yeah.
I don't really push myself to do that on my own, yeah, but there's like a little bit of encouragement.
Yeah, the main class
Start
that
yelling,
That was
start
just-
screaming.
Yes, so yelling? No?
the But the main class that I need this for is the math class, because I don't understand that teacher very well. And I take the board a lot.
It was really good.
Good.
Yeah, it was hard, but
You get credit for it?
yeah, I got credit for it.
Right.
And yeah, and it sounded like towards the end, we're like, oh, now we have to hold on environment.
They should be staying on, and if they have a 10
For
minute
what,
walk,
for
even
For a
for
good
For medicine? Okay.
Yeah, so I guess I didn't use that, but I still needed the
Yeah.
Yeah, but it was good, I recommend it. Like,
Cool.
I'll try and call them,
Yeah,
the
they
class,
do it,
if I
like,
stop by
every
or out here, lab.
Nice. Well, we're doing
lab is
our
only on
This is
Tuesday,
very much
so for the
low
rest of the day,
Yeah.
This fall or this winter
I'm
here.
pretty
Oh, you are?
clear, I do have like,
So you haven't had that
appointment,
conversation.
like with someone to study in the library at 1.
Okay, just, yeah, we got here at 10.
Yeah.
10:30, 11.
Yeah, 10.
Okay,
Yeah.
just come back up to my office,
Funny was like,
and then
the
we're
library
gonna
really
look at it,
usually
and
like
come back
going
on.
at one.
And then I'm gonna call them and tell them that they can't get off for these 10-minute breaks, or they need to stay.
But if there's
They're
something-
charging
I
us
don't
$2
isolate
maintenance fees, whether it's working or not, they need to stay on.
Alright, okay, I just said like, don't test out if you're not going extra.
I like that class a lot, she's not the UCSD one, but, when I took bio, I liked it so much I voluntarily as an elective, molecular biology, 7 a.m. lecture. Which I didn't make all of those, but I mean, I wanted to bring my GPA down, I got to be in that one just because it was elective anyway. But I liked it that much, I thought it was that cool that it was taking that class, so.
Yeah. It was very interesting. A lot to memorize, but really.
Yes.
Really good.
Exactly.
I'm looking at that. That's like funny, and I wrote something in the full meeting.
I locked in Saturday, Santa Cruz.
Oh, you are gonna
Finished
go?
on the first 5 minutes, 8 o'clock, I was doing the gravel break, because 8 o'clock all the new sites come up.
Yeah. Oh, that's good.
I got shafted yesterday because, somebody beat me to it while I was on the phone, trying to talk to the operator. So this morning I thought, I'm just gonna come here.
Yeah.
But then there's the password trucks. What's your password? Password changed. So I was like, no! Every little second, it's just, clock is ticking.
That'd be nice to get out of the smoke a little bit. I heard
Yeah.
that people might have to leave again.
Christmas
In
Valley, right?
Christmas Valley, yeah, they said made a run in Christmas Valley again.
Yes.
Oh, God.
But the other side is that while you stay, you have to get hell smoke and feel sick, and it's like,
Right. It'd just be nice to have one normal weekend in here somewhere, right?
Northland will do it.
Hopefully,
More east way, I guess.
yeah. All right, well, we still have a couple people on their way back, but while we're working on that, or while we're waiting on them, you guys can start working on this. And remember that the electron geometry is really a one-to-one correlation. It's a direct translation of hybridization. Hybridization is the math that happens, that we use to describe these orbitals. Electron geometry is what we can actually measure in a lab, because we can do X-ray crystallography on these compounds and see exactly where every nucleus is in its most stable state, which means we can, we can confirm what Linus Pauling was saying. And really, X-ray crystallography was in its infancy at the same time Pauling was coming up with his idea. So it was really happening at the same time, which was really, really exciting, because he was able to come up with these really cool ideas mathematically. Say, well, this is how you get your lowest energy system. And at the same time, in the lab, the X-ray crystallographers were saying, well, we can do that. We can see where all the atoms are. We know exactly where all the atoms are. So we can, and it matches up really, really well. And just side note also that one of the other interesting things that Pauling did was he's actually responsible for the popularization of vitamin C as a dietary supplement. He was a huge proponent of the anytime I get sick, I take 1,000% of my RDA of vitamin C, which is not very scientific of him because it doesn't all get absorbed anyway. You just want to pee in most of it out. But that you can trace emergency and airborne basically directly back to Linus Pauling in the 60s.
He's the reason behind my kidney stones last season.
Yeah, exactly.
Ascorbic acid in the renal system.
Yeah, exactly. So he wasn't right about that, but that's not what he won his Nobel Prize for. So we can give him a pass on that
Yeah,
one.
we give credit.
All right, so all we're looking for hybridization, we don't need to actually have the molecular orbitals drawn. All we need to know is how many electron groups there are around it, how many sigma bonds there are. Sigma bonds are lone pairs. Any sigma bond or lone pair is going to be one orbital that has to be hybridized. So a carbon with 4 bonds is always going to be 4 single bonds. It's always sp3. Right? And that means we also know the electron geometry of all of those as well. We know the shape and where we're going to see these bonds forming. Because everything that's sp3 is going to be tetrahedral. Right? And tetrahedrals that, I threw the other shapes on here just so you remember that they exist. But really we're interested in tetrahedral, trigonal planar, and linear are going to be the geometries we deal with in this class. There might be a time when we have to reference one of these other geometries in terms of a catalyst. We're using a metal as a catalyst. But typically speaking, we're only going to see tetrahedral, planar, linear. Right, so yeah, tetrahedral is a little bit tricky to wrap your head around. It's the one that doesn't have nice, clean angle numbers. It's 109.5, and even that's approximate. But it's not, once you get the hang of it, it's not that hard to visualize. Right, a tetrahedron is a 3-dimensional, or is a 4-sided die, a D4. You play Dungeons and Dragons. Yeah. Yeah, this shape. In Dungeons and Dragons, each corner is labeled with the number 1 through 4, right? So you can roll it. But in this case, you have carbon in the middle, and then do CH4, you have hydrogen at each of the corners. And that's the shape that we're looking at here. And just a reminder that the easiest way to draw a tetrahedral geometry is always using those wedges and dashes. If you there's any number of ways you can do it. What I usually find the easiest is if you put 2 of the bonds flat in the plane of the board, about 120 degrees from each other. The other 2 are going to be also about 120 degrees, but one into the board, one out of the board. Right, so it's almost like an equilateral triangle, except on one of the corners, you've also got one into the board and out of the board. And you can also do weird things like see that in biology a fair bit when they're drawing. They don't actually draw the wedges and the dashes, but when they're drawing carbohydrates, a lot of times you'll see them, and it's implied that the horizontal bonds are coming towards you and the vertical bonds are going away from you. That's also a tetrahedral structure. You can use your imagination or your 2 hands. If you take these 2 fingers, if you're like me, you can get them almost 120 degrees apart from each other and put them together like this. Your thumbs and your fingers represent the hydrogens, where the atoms are going to be. So if you think about this as being the ones pointed towards you, those are the ones pointed away from you. It's still tetrahedral shape. I find this easier to visualize and draw. All right, what are the other hybridizations? We found all of the sp3s just by looking for carbons with 4 bonds. sp2, 1 pi bond, so 1 unhybridized p orbital. So both of these are going to be sp2. These are both going to be sp, right? Are the hydrogens hybridized? Why not?
They don't have anything to hybridize.
They don't have any of their orbitals to hybridize, right? They just have an s orbital. So yeah, that's exactly right. So hydrogens will never be hybridized because they only have an s orbital to work with. Everything that has a more complicated geometry is going to have some sort of hybridization. I think I could say everything. Everything with p orbitals involved, basically, is going to have some sort of hybridization.
So everything on the last column, the periodic table that has full valence, this doesn't apply to them all.
So this only starts applying when we start making covalent bonds. If you don't have covalent bonds, then everything stays in the atomic orbitals as opposed to the hybridized orbitals. So yes, so neon, argon, helium especially, as you get to actually further down, some of the noble gases actually can start making covalent bonds, and you start seeing some of these complicated geometries, some of the stuff like this. So you do start seeing some hybridization, but only when you put it with something that's really, really electronegative, like fluorine. If you put xenon with fluorine gas, you'll actually wind up with a combination of xenon tetrafluoride and xenon difluoride, I think, where you will have some sort of hybridization happening. But yes, that idea that we're not limited to atomic orbitals. The atomic orbitals, as long as we're talking about individual atoms, the atomic orbitals work great. That's a perfect way of calculating energy and visualizing orbitals and stuff like that. But the second you make a bond, that all goes out the window. Right, and so here's a better view of an sp carbon. This is acetylene, actually, so it's carbon triple bonded to another carbon with a hydrogen on each side. So acetylene is just this compound, C2H2. And the orbitals look like this. You've got one pi bond that's coming this way, and then perpendicular to that, you have another pi bond. And so you can't really ever have a quadruple bond between carbons. Seems like, well, carbon it needs 4 bonds, and it can make single bonds, double bonds, triple bonds. Why not quadruple bonds? Well, because the physics of this, and actually in the geometry, is that last p orbital is already pointed in the same direction as the sigma bond, right? So you actually can't get that third p orbital to be part of a pi bond because that space is already taken up. There are some, if you get into some of the metals, you can actually get quadruple bonds forming, or even things that have 7 electron groups around them when you start getting into some of those bigger orbitals, but not when we're talking about carbon. All right. When you form more than one bond between 2 nuclei, are the nuclei going to be closer together, the same distance, or further apart? Is a pi bond going to affect the bond distance at all? Why not?
Because it's going to be either up and down or back and forth. It's not going to affect the linear distance between the nuclei.
Okay, so that makes sense when you put it that way, right? Trouble is you still need to get these 2 p orbitals to overlap, right? This is still an attractive force to get these things to pull together. So pi bonds are still an attractive force, and that attractive force will pull the carbons slightly closer together. Not as much as a sigma bond versus no bond at all, but pi bonds are shorter. If you have a sigma bond and a pi bond, the distance will be smaller than no pi bond because these don't overlap as well. So to get these figure 8s to overlap, you have to get these carbons closer together in order to get any overlap. Right? And so if we do it, and then we extend that, if we have two of these pi bonds, they're going to go even tighter. The bond distance in acetylene is shorter than ethylene, which is when there's one pi bond, and it's shorter than ethane, which is just sigma bonds. Right? So the more bonds you have, the tighter everything gets pulled together, which, you know, you can argue it from both directions. It seems like there's no implicit force pulling things together, but remember, you need orbital overlap for things to happen.
I mean, wouldn't that be electromagnetic though, in that instance, because they want to share the electron?
It is, yeah. So it's a result of electromagnetic force pulling these. In order to make a pi bond, you need enough of orbital overlap. So yes, you're right.
So in the diagram, it doesn't look like they're overlapping, but are you saying they're like being pulled together and overlapping like eventually, or is it something that the diagram can't show?
Let's see if there's another image that'll show it. That one's a little bit closer. You can still kind of see the shape of the individual orbitals here, but they kind of like smear out as a way of, because they don't stay in their original p orbital shape. I said that they don't hybridize, but they kind of hybridize with the other p orbital. So they kind of smear themselves out so that you can kind of get back and forth between those two things. And so sometimes they get drawn in a way that looks like that. I've had students call it an upside down canoe or vampire teeth. But it's still a p orbital shape, and you're still going to have that phase where you've got different colors on each side. And there's still something of a p orbital shape to it, just like there's still something of a p orbital shape to a sigma bond too. Right? Because all we're really doing is we're mixing these two functions together, so all you can get are the things that are components of those two functions. It's going to look like part of both of those. But for a lot of figures, it's easier to draw them just like this, because if you try and draw this with all of the other orbitals at the same time, it gets really messy really fast. Especially if you only have one color that shows up on the camera. If you have multiple colors, you can make it look cool and label everything properly. But if you form pi bonds between two nuclei, is the bond energy holding those two nuclei together going to be smaller, the same, or larger?
It would be larger.
Yeah, that makes a lot of sense, right? It's kind of intuitive that way. If you have three bonds holding two atoms together, it's going to be harder to pull those two atoms apart compared to when it was only one bond. It's not going to be, if you have a triple bond, it's not going to be triple the original bond energy, because pi bonds aren't as strong as sigma bonds. They don't have as much overlap, like we already talked about, right? So pi bonds are not as stable as sigma bonds. Sigma bonds are more stable because you've got more direct orbital overlap. Pi bonds are better than no bond at all. They're better than having an incomplete valence, but they're not as good as a sigma bond. So that winds up being something that we differentiate between the two types of bonds, because a carbon-carbon sigma bond is not the same energy as a carbon-carbon pi bond. Both of the carbon-carbon pi bonds are the same energy as each other.
It sort of seems like with acetylene, for example, it's like relatively unstable compared to the corresponding alkaline. So
Yeah.
Is that because of the increased bond energy?
It's a little bit of both. So there's more pure bond energy in the molecule. So carbon-hydrogen bonds are stable. They're sigma bonds. They're pretty stable. If you burn it, then ethane puts out, I think actually per mole, ethane puts out more energy than acetylene. But acetylene has other properties that make it more advantageous for things like welding. in that you can get it to burn at really, really high concentrated pressures, and still burn completely. If you try to compress ethane, which is basically natural gas, to the same pressures as you use in acetylene, it doesn't react the same way. Partly because there's more energy in the ethane, but the individual bonds are more stable as they are until you get it to burn. Acetylene has these pi bonds that are pretty easy to start the process. They go really fast to break those pi bonds and start making carbon-oxygen bonds. So it's a combination of reasons why, but in general, double bonds are going to be less stable than single bonds. Even if you can break in the real world or in the biochemical sense, if you break a carbon-hydrogen bond, that's more energy than a carbon-carbon pi bond. But it's harder to break. It's harder to get it because it's starting from a sigma bond that's more stable. I think I can say this. I'm not up on my well. I haven't taken the class in welding in a really long time. But I believe that acetylene burns faster, which allows you to get to higher temperatures in welding. Ethane burns slower, but has more energy in it per mole. So that's why natural gas, ethane is a really good source of natural gas when you're just cooking, when you only need to get up to, 400 Celsius as opposed to needing to get up to 1200 Celsius, which I think is where acetylene burns, somewhere in there. And we can actually measure those bond angles, and we can actually calculate them as well. Brad, did you have a question?
Yeah, so are pi and sigma bonds at different energy levels?
They are, yeah. Sigma bonds are going to be more stable, so they will be lower. When you start looking at molecular orbitals, as opposed to even just these hybridized orbitals, you wind up with everything sort of shifts up and down a lot as you start making these bonds. And so it starts looking really, really complicated, and we'll stop looking at molecular orbital diagrams for anything that's where we have bonds happening. Basically, we'll just look at the hybridization instead.
And so is that also a reason why the phase changes for each overlap? If that makes sense? Because there are different.
Say that again?
So you know how you said that there's the constructive and destructive interference? Because these bonds are at different energy levels, that'll change the properties of the wave function trees, right? And that's why there is the constructive or destructive interference, right?
So the constructive and the destructive interference is a result just of the function itself. The function has a positive on one side and a negative on the other, just like up and down with a wave, right?
Sure.
The hybridization is affected by the phase, but the phase is really just an implicit part of the function that makes up these atomic orbitals. It's just sort of built into the function itself.
Okay.
Remember the guitar demonstration with the waves? You added the harmonics, you added nodes. If you have a node, that means you have to have a positive on one side and a negative on the other. If you don't have a node, then that's just one uniform wave, basically. But the second you add a node to it, in order for it to be up here, it has to be down there.
Yeah.
And so that's where the phase comes from with those atomic orbitals.
Got it. Okay.
All right. Let's remind ourselves about polarity and how electronegativity works. So we've been talking all day about 3D structures, and you guys have seen Vesper geometries before. We've been practicing thinking about things in 3D. So I think that the asymmetry part of polarity might actually even be easier now that you've been thinking about these things in 3D. And in general, we wind up with symmetry winds up mattering a lot less in organic chemistry than in Gen Chem. In Gen Chem, when you're dealing with only one central molecule, there are a lot of different possible symmetric structures you could draw. The second you start having two carbons, the odds that you're going to get a completely symmetric molecule are really, really small. And even if you do get a completely symmetric molecule, like for instance, All right, this isn't completely symmetric, but it seems symmetric at first glance. That's acetone. This seems like, well, it's got, it's the same on both sides. It should be symmetric, right? But the fact is that because there's oxygen more on one side than the other, it's still going to be a polar molecule. So for the most part, and especially once you start being able to take these things and twist them around in different configurations, all symmetry goes away, basically. And so when we're talking about polar molecules in OChem, we're predominantly going to be looking at how many polar bonds do I have versus how many carbons do I have. Because essentially, anytime you can point to a polar bond, that's one part of the molecule that's going to be polar. But almost always in OChem, the rest of the molecule is going to be non-polar. It's going to be all carbons and hydrogens or carbon-carbon bonds. So in order to really discuss polarity, it's not just about, well, is it asymmetric? It's also, if we're talking about it in the sense of, can I use this as a polar solvent to mix with water or to dissolve something that's polar? We're going to be looking at it in terms of how many oxygens do I have relative to the number of carbons. Because oxygens and nitrogens, remember our big four for polarity or for electronegativity was this corner right here, right? Nitrogen, oxygen, fluorine, chlorine. We'll deal with nitrogens a little bit, but mostly as we get further on in the course. Oxygens and these halogens, for now, are going to be the ones that we think of as making a polar molecule. And you can see things. Let's see what I had in the next slide before I just start talking out of that, making things up. So the more polar a bond is, the more polar the molecule is going to be in general. So in polarity in a bond is just difference in electronegativity. So the larger the difference in electronegativity, the more polar that bond will be. So this is fluoromethane. That's a fluorine attached to a carbon, carbon attached to hydrogens. Carbons to hydrogens, that's a non-polar bond. It's very slightly polar. There's a very slight difference in the electronegativity. But for the sake of this class, that's sort of our definition of a non-polar bond. And these partial charges that we get on either side of a polar bond are going to tell us basically where the electron density is. It's not always going to be where there are lone pairs. You can have compounds that have lone pairs and there's a partial positive on that lone pair, which seems like it's a contradiction. But really what we're talking about is that half of the molecule is missing electron density despite the fact there's a lone pair there. So for instance, if we look at nitrogen with 3 fluorines attached to it, if it's neutral, then it has a lone pair up here, right? But all 3 of those fluorines, fluorine is the most electronegative element. So all 3 of those fluorines are pulling electron density downward. So even though there's a lone pair there, the nitrogen itself, we say that it has a partial positive. And so we want to know where the lone pairs are, but we also don't want to know what's strongest in pulling electrons away from lone pairs sometimes. This is a slide on practicing finding out if things are polar or if these molecules are polar. I'm going to skip over this in the interest of time. There's more practice. Just remember, we're looking for, if you've got one of the big 4 attached to a carbon or a hydrogen, it's polar. That's a polar bond. Other cases, those are the most common cases. If it's something else, you're going to want to look up an electronegativity and see if it's polar or not. But so carbon attached to chlorine is a polar bond. But this was one of my examples of something that has symmetry. It has 4 carbons or chlorines attached to the carbon. So all of them are pulling in exactly opposite directions. You can actually do the vector map with it and break down the forces on the electrons, and they wind up canceling each other out exactly. Because all 4 of those chlorines are going to be pointed in the exact opposite directions as the other 3. But any other time you're going to have carbon-oxygen bonds or carbon-hydrogen bonds, it's going to be a polar molecule. And the more polar the bonds, the more polar the molecule. All right, just so we can, so you're familiar with all of these before the quiz this weekend. I'll go through and I'll make sure the quiz doesn't get to anything we didn't get to. I want to talk about the different ways of drawing things, and this should match up with some of the language and some of the things you were working on in lab on Tuesday. The Lewis structure is, nobody in OChem really calls it the Lewis structure, we call it the complete structure. Complete structure means you're drawing every bond, every carbon-hydrogen bond, every lone pair, you're showing exactly where everything is. It's not always the most accurate representation though, because usually we do it at 90 degrees to everything instead of actually showing the tetrahedral structure for the sake of fitting it on a page and not overlapping things. Partially condensed structure, or the Cooley structure, it basically just means that we're showing bonds between what we call the heavy atoms. Heavy atoms is anything that's not hydrogen. So you show the bonds between the heavy atoms, and then you just sort of write the right number of hydrogens next to it. So sort of a hybrid version of the complete structure and the condensed structure. The condensed structure is just going to be writing it all with subscripts. It gets really tricky for these three-dimensional molecules when you start adding branches. You start having to do things like CH3 attached to this carbon. That's two CH3s attached to the middle carbon, which then has a hydrogen and an oxygen attached to it. And least helpful in organic chemistry is the molecular formula, because the molecular formula could really be any number of things mixed together. And that's essentially what you're, when you buy gasoline, for the most part, at least originally when in its most pure state, it was just a mixture of things, of hydrocarbons that all boiled at about the same temperature. And so it was a mixture of a whole bunch of things that most of them had about 8 carbons total, which is why we use octane as our reference. But they can be arranged in any number of ways. There's any number of constitutional isomers you could have with 8 carbons, right? And so really, when you have that, you just have a mixture of everything. So they might even just sell it. You could even sell it as mixed octanes or mixed hexanes. Just means it's a bunch of stuff that's got 6 carbons, but it's all of the different constitutional isomers mixed together. Right, so we're going to avoid the molecular formula in general, other than as a way to, well, it's in lab, it's actually really common though, because you can actually say, well, I can burn this and collect the CO2 I get, and I know I get this many moles of CO2. Therefore, I know I have this many moles of carbon in the original structure. I don't know what it is, but I know how many carbons there are in it. So it can be helpful, but it's not giving you the real structure at all. So it's really sort of a starting point. Especially historically. One of my favorite classes in college was called Organic Qualitative Analysis, which was basically, here's an organic compound, what is it? Here's a white powder, tell me what it is. And so we basically, it was a senior level class. They basically just turned us loose in the chemistry department. We had a week. Every lab was, here's another unknown, what is it? And our final exam was 2 unknowns mixed together. Find a way to separate them and then tell me what both of them are. I got really lucky with that one. One of mine dissolved in water, the other one didn't. That made it really easy to separate them. But all this to say that the molecular formula is not all that helpful necessarily, except as a starting point. All right, so here is practice just doing complete structures. If you start from a condensed structure, can you draw the complete structure? So let's practice with some of these. Remember, all carbons are going to have 4 bonds, no more than 4. The number of the counting shall be 4. last year, the ongoing joke was, I'm trying to teach you to count to 4, but not 5. Never count to 5. 5 is a bad number in organic chemistry. So when you're starting from the condensed structure, it's not necessarily always a direct translation, but it's a matter of, okay, well, I know that these are the pieces, and I know that this is the approximate order that they're attached in, but I also know I need all my carbons to have 4 bonds and all my oxygens to have 2. Right, so it doesn't explicitly tell us necessarily. Sometimes this oxygen that's in the middle like this might be an OH hanging off the side or something. But there's no way to do that would still leave the carbon with 4 bonds necessarily. So this is the only one that makes sense based on what we're looking at there. So when you're trying to go from condensed structure to complete or vice versa, do the best you can and try to make it so that there's no way of misinterpreting it. Make it unambiguous. It's more important than this is the exact strict order that you are to write things down in. And if it was an OH hanging off of a carbon, it would be written like this. It would be written as OH, not HO. The fact that the H comes right after the carbon tells us that it's directly attached to the carbon. The oxygen can't be attached to the hydrogen, so it must also be attached to the carbon.
Are we missing one more hydrogen on that last carbon?
Yes. I wondered why it wasn't crowded over there. Thank you. And so if we have something that looks like more like this, you have CH3, CH2, and parentheses 2. That means we have 2 of these 2 carbon groups attached to the 3rd carbon. They're both attached to this 3rd carbon. So we say it's CH, there's going to be one CH3, CH2, and then there's going to be another one of those. All right, so that takes us to right here. This carbon has another hydrogen, and then some more carbons. So one hydrogen attached to the 3rd carbon, and then CH2, CH2, OH. So CH2, CH2, OH.
going about this, do you recommend starting with the carbon chain?
Condensed structure is a little bit tricky. Yes, the main thing you want to do, if you start with the carbon chain and get the primary carbon chain in there, you want to just make sure you don't forget to go back and add that second 2-carbon group. So because there's 2 carbons at the very beginning of this one, I don't want to forget that, so that's why I did both of them at the same time at the beginning. But as long as you're checking your work and going back and looking at it again, then just getting all of the carbons in a row and then adding the branches is fine. If you're going from the name to the structure, that's actually the way it's recommended. Draw your base molecule first and then start adding all the, my OChem instructor used to call it spinach. Add all the spinach hanging off the side. I don't know where that comes from, but apparently it's like an actual thing in people who learned OChem in the 60s. That was a common term. I've seen it shown up in textbooks too. I don't know why, but that's a term that's used. Ryan?
Sean, do we want to get in the habit of drawing out the H, or can we just draw a line?
So until I'm convinced that you can count to 4 but not 5, I'm going to have you draw all the hydrogens.
Okay.
Once you get good at it, we'll just start going to skeletal, and we won't even draw lines for the hydrogens. We'll just go, do this, because if there's nothing drawn attached to it, then you know that you have as many hydrogens as necessary to make it 4 bonds. But while we're still practicing it, we're going to draw everything.
Figured there was a method to your madness, that makes sense.
Usually, it's something I've at least thought about. It's not necessarily that I've landed on the right solution to teaching it, so I'm always open. All right, we're already 2 minutes over. We'll end there. The quiz is going to be some stuff on polarity and hybridization, and maybe a little bit on drawing structures from the formula or vice versa. Maybe drawing some isomers, that kind of thing, stuff we practiced today. All right, any questions? All right, good first week, everyone. Cody, make sure you get that application in date to HR.
Yeah, I'm waiting on my 3rd reference in the email address. I've got the first 2 references, everything, just waiting on.
Okay, great. Glad to hear it.
Yeah, I was slacking on it. I need to do it right away.
And no worries, HR is swamped this week anyway, so.
Yeah, I'm hoping I'll text you back today and I'll be able to get that in this afternoon.
I just took one back.
Might just try to rally up another one too, just in case.
You can either do that, or if they don't get back to you, just use me.
Oh yeah, that's it, good.
Yeah,
Cool, thank you.
I'm the one who's telling you to apply for the job, right? I think that qualifies as a reference.
I appreciate it, thanks, man.
No problem.
Yeah, I'll have that done in a few minutes then. See you next week.
Yeah.
Great weekend.
I'll see you Tuesday.
Can you get the microphone there?
Yes, thank you. Did it ever wind up working?
No, it was constantly going in and out, or just
Okay,
cutting off. So,
Maybe try to help out.
going through here today to
Yeah.
try and fix
Maybe
it.
you can do it.
The captioner said, I think you're doing everything right, you might just be using right.
Okay.
That's exciting, man.
But yeah, it's the first week, and I'm really glad that I'm figuring it out now.
Yes. Well, and if you want to, before lecture next week, if you have time on Monday, or I would always try to get here at 4:45, but it's sometimes that doesn't always give enough time, and sometimes I'm late.
Yeah.
But if you wanted to set up a time with the captioner on Monday to come in and see me, to give it a try, I'm free after 1 or before my office hours are 9 to 10:30.
I think the captioner works remotely, so it's kind of like I came in here early today to try to figure it out, but they weren't online until the process was started.
It builds up.
But just if if there's a way to test it ahead of time, then by all means, we can test it. If there's not, then we'll just try it again.
Yeah, thank you for offering that. right now, they should still be online. My computer died, but I'm gonna go to the DRC and we're gonna try to fix it there.